Right, here we are, guys, with FBF.2 Learning Target 2.2. Okay, now we're going to create an explicit formula from a pattern. So whether that pattern is given in numbers, whether it's given in picture form, that's what we're taking a look at. Okay. Now, the thing to remember about explicit formulas, okay, is that they connect inputs to outputs. So the idea here is that, if we think in terms of a table with our input and our output, so our equation has to have both of these, a variable and the a sub n. Okay. Now the output is generally what we're equal to. Okay. And in this case, the way we're doing it, it'll always be. So then we have to have somewhere this n that will connect the number here with the number we get here. Okay. So to do that, it's all about where we start, okay, that zero term, and then how it's growing, and that repeated growth, okay? So in arithmetic, it's going to look like this. So our start number, also known as our zero term, okay? And we're going to either add or subtract by that common difference. The common difference is how it's growing, if it's adding or subtracting or anything like that. For example, if we look at number 1, negative 28 to positive 2 to positive 32 to positive 62, our growth is definitely adding 30 here, so it's arithmetic. Okay, so that common difference would be plus 30. Okay, now we're repeatedly adding that 30 right down here. Okay, so repeated addition, the way we talk about repeated addition is through multiplication. Okay, 30 plus 30 is the same as 2 times 30. Okay, because there's 2 of them. So if we don't know how many 30s we have, we multiply by our variable n, which stands in for that input, because the number we have here tells us how many times we add over here on the output. Okay, so then, looking back here at ours, if we go backwards to the zero term, okay, so negative 28 minus 30 would give us negative 58. So that's where we started, and there's our arithmetic version of it. Okay, so looking back here, a sub n equals negative 58. Then we're adding 30, how many times? N amount of times. So that n is multiplied by the 30. Now if we drop down here to let's look at number 8. I go 2, 6, 18, 54. So here we're times them by 3 each time. Okay, so that's geometric. So if we look at the explicit, our geometric version, okay, starts out exactly the same. It's still connecting the input to the outputs. We're still dealing with growth. We're still looking at our inputs. Okay, so we still have our start or our zero term. Okay, but this time we're going to multiply. Now, geometric is multiply and divide, but when it comes to the explicit, we only multiply. So in the case of if we were dividing by 3, that becomes timesing by 1/3. If we're dividing by 2, timesing by 1/2. If we're dividing by 4, timesing by 1/4. And you get the gist with it, right? So we're multiplying by that constant ratio. And then, because we're doing repeated multiplication, okay, that turns into exponents. That's how we write repeated multiplication. So in this case, we're timesing by 3 repeatedly, right? If I go 3 times 3, that's the same as 3 squared. Okay, that 2 represents a number. If we don't know how many times we do it, we get that n as an exponent. Okay, so if we're looking back at this example that we have, we're timesing by 3. Okay, so going backwards, we would have started out with 2/3 or 0.6 repeated. So we start at 2/3. We're repeatedly timesing by 3, so we make that our exponent. And that's what a geometric one looks like. So in this case, that's what our problem would look like. Now, the biggest mistake I see is people adding and then putting the variable up top, or timesing and putting the variable down low. Okay, completely changes because This means repeated multiplication has to be an exponent. Repeated addition has to be timesing by the variable. Okay? So, let's take a look. Now let's actually look at number 7 while we're on this geometric, because if you notice, it starts out big and goes down. Okay? We're actually dividing by 4 here each time. Okay? So going backwards, timesing by 4, we'd start at 256. So I'd go a sub n equals my start, 256, but I can't go divide by 4 to the n. That doesn't work mathematically. So instead of dividing by 4, I'm timesing by its reciprocal. Well, 4 over 1 would be the fraction, its reciprocal 1/4, so I times by 1/4 to the power. Okay? And that's kind of what we have to do on those types. All right? Okay, well, why don't we just finish these geometric ones. So 4 to 16 to 64 to negative 256. When we go positive to negative, we know we're timesing by a negative. 4 to 16, I have times by negative 4. Does that give me the positive 64? Yep, it does. So going backwards, 4 divided by negative 4 would give me negative 1. So a sub n equals my start, negative 1, times negative 4, my growth. And I like to put that in parentheses, and then to the nth power. Okay? Oh, one more thing to mention. We do see these explicit equations a lot of different ways. We can do f of n equals the stuff, zero term plus common difference times n. We can do f of x, zero term times constant ratio to the x power. Make sure whatever's in here, if you're using the function notation style, matches the same variable. We can even on these, we use y a lot too, okay? zt plus cd, and you can times by n or x. In this case, it really doesn't matter what variables you use, okay? Or the same idea when we're dealing with our geometric version. Okay, so you're welcome to use that different style if you would like. But I'm going to just use the a sub n because that's kind of what we've been using. All right, number 10, 2 to 4 to 8 to 16. Well, 2 plus 2 would get us 4, but 4 plus 2 would not get us 8. It'd have to be 4 plus 4, which tells me I'm doubling. So I'm timesing by 2. Okay, going backwards, 2 divided by 2 would be 1, and 1 times 2 is 2. So we start with 1, then we times by 2, and because it's repeated multiplication, that becomes our power, and we call that good. All right, looking at number 11. Negative 3 to 9 to negative 27. Again, we've got the negatives. 3 to 9, we're times them by a negative 3. 9 to negative 27, definitely times them by a negative 3 each time. Going backwards, negative 3 divided by negative 3, because it wouldn't be 0, becomes 1, positive. So a sub n equals my start, 1 times my negative 3. Raise that to the n power. Okay, number 12, negative 2 times negative 6 times negative 18. So they all stay negative. So I'm times them by a positive 3 in this case, repeatedly. Going backwards, negative 2 divided by 3 is negative 2/3 or negative 0.6 repeated. So whether I do it with a decimal or a fraction, it doesn't matter. So negative 0.6 times 3 to the n. Okay? Works either way. All right, so let's take a look at the rest of these arithmetic ones. Okay? So again, arithmetic, we look for the pattern. 30 to 24 to 18, we're subtracting by 6 each time. So a sub n equals, going backwards, we'd have to start at 36 to get 30 when we subtract 6. So I start at 36, then I minus 6, and I times that by n. Okay? Also, something to probably note, let's look at 3 for this part. How is it grown here? Looks like we are adding 7 each time. Okay, now we normally go back here to the 0 term, right? And I like this better, but you could actually start with the first term. Okay, and I've talked about that with recursive, that it's really easy to start. Instead of a sub 0, you just do a sub 1. But we don't have that because we're not doing recursive. You can kind of do a similar thing. The problem with it is if I don't start with the 0 term, that puts me off by 1. Okay? Because I talked how whatever number our input is, that's how many times we're adding, subtracting, or multiplying. Okay? Well, if we start 1 lower, then we're 1 lower, and we have to subtract 1 to get us back to the 0 term. So I could start with 12 and add 7, but instead of multiplying by n, I would multiply by n minus 1. Okay? So that's if you start with, instead of the 0 term, the first term, that's when you would include that. And if I honestly look at this, if I distribute that, I get 7n minus 7 plus 12. 12 minus 7 gives me 5. So it's still the same equation, it's just off 1 slightly. So I personally don't like to do it that way, but you sometimes may see it, especially with these ones. Like if I look at number 8, okay, maybe I don't like having to have the fraction, but if I started with the first term, okay, it looks a lot nicer, doesn't it? The problem is I'm off 1, so I have to go n minus 1 as my power, okay? Which sometimes some people like that better for the geometric. I personally don't, but there's that option there in case you want it. Okay? All right. 4. Negative 26 to negative 34 to negative 42 to negative 50. We are definitely adding 8 each time. Okay? Actually subtracting 8, aren't we? So I'd go a sub n equals, going backwards, what negative 26 plus 8 would give us negative 18. So negative 18 minus 8 is negative 26. So we start at negative 18, we're subtracting 8, and we're doing it repeatedly, so times n. Okay, number 5, 38 to 40 to 42 to 44, definitely subtracting 2 each time. So a sub n equals, going backwards, we would start at negative 36 and subtract 2 each time. Make sure that your variable is always going with the growth, not with the start. And hopefully you like doing the explicit. There's other ways to do the explicit, but I love this way just because whether it's geometric or arithmetic, I still treat it the same way. The only difference is whether I'm subtracting or adding, and either if I'm multiplying or taking it to a power. Number 6, 17 to 20 to 23. We are adding 3 each time. Going backwards, that would have a start at 14. So a sub n equals 14 plus 3. And 3 is repeated, so we times it by n. Alright? So that's with our sequences. Now, if we're given a picture, we can treat it the same way. Okay? The thing that we have to notice is if it tells us it's the first, okay, we treat that as the first term. If it says it's at the beginning, then we can treat that at the 0 term. If it doesn't tell us at all, which I think all of these tell us, then we generally assume that this is the first term. Okay, in some cases, like 20, we'll deal with that one differently. Okay, and it's kind of because of the context of that visual. Okay, so we want to get back to step 0. So first, let's find the growth. So we have 1 at step 1, 4 at step 2, and 7 at step 3. We can definitely see we're adding 3 boxes each time. So we're adding 3. What plus 3 would be 1? Would definitely be negative 2. So we start at negative 2, and we're adding 3. It's arithmetic because we're adding, so we times by the variable. Okay, number 14. Now we've got an at the beginning, so I can just go a sub n equals 1 because that's our beginning. Then we're going to 5. Then we are going to 9. Looks like we're adding 4 dots each time, so plus 4, which we do it repeatedly, so times n. Okay, number 15, we're counting the number of sides and middles. So 1, 2, 3, 4, 5, 6 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, looks like we're adding by 10 maybe, but let's double check. It may not be arithmetic. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, so 11. 1, 2, 3, 4, 5, so 16. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, so 26 definitely. You'll notice when we add we just add 5 more sides, and we're adding it twice, so that would be 10. So definitely plus 10. Going backwards to the 0 term, we'd minus 10, so we get negative 4, which doesn't make sense according to our figure. That's why some people like to do the first term, not the 0 term. But mathematically, this is how we have to do it to make it work. Again, where we start, how it's growing, because it's arithmetic, timesing by n. Okay, number 16, we have 1, then 3, then 5, then 7. So we are definitely adding by 2. So going backwards, we would start at negative 1. So a sub n equals negative 1 plus 2. It's arithmetic, so times 2. Okay? Hopefully this is seeming a lot easier to deal with. Okay? So looking at 17, we start out with 3, and that's at the beginning, so I know that's my 0 term. So a sub n equals my 0 term, 3. So I start with 3, then I get 6, then I get 12, so I'm definitely not adding 3. I'm timesing by 2. Because it's repeated multiplication, now my exponent goes up top. And there's my explicit geometric equation. Okay, looking at 18, we've got our first term, second, third. So we have 1, 4, and then 16. So we could be adding 3, but that won't get you to 16, so we definitely have to be timesing by 4. Okay, now if we go back, 1 divided by 4 would give us 1/4, or 0.25. So I can do that, or this is a case where I could say, let's use the first term instead, and I start with my first term, I'm timesing by 4, but to get back to my 0 term, I have to minus 1. So you could do it that way, or you could do it this way. Do the 0.25 times 4 to the n, or 1/4 times 4 to the n. Okay, number 19, we have 1 for our first term. Second term, we have 2. Third term, we have 4. So again, going back to the 0 term, looks like we're timesing by 2. Because we'd have to add 1 then 2, so definitely doubling it. So that would be 1/2. Again, you could try to do it like this and go a sub n equals 1 times 2 to the n minus 1. But I like to start with the 1/2 times 2 to the n. To me, it just looks cleaner and nicer and better. Okay, now 20 doesn't say it's the beginning. However, if you know anything about tournaments, okay, because that's what we're dealing with here, okay, is we're starting with 32 teams, okay. We always show the whole graphic. Okay, we don't have an imaginary one here. So we're going to call this our 0 term, then our 0 round. Then after the first round, we're down to 16 teams, if we count them. Then after the second round, we're down to 8. At the third round, we're down to 4. Fourth round, we're down to 2. And the fifth round, we've got our winner at 1. Okay, so we're definitely dividing by 2. But, just like over here, okay, we don't divide, we times by the reciprocal. So the reciprocal of 2 is 1/2. So I'm timesing by 1/2. So a sub n equals my start of 32 times 1/2. That's my growth. Take it to the nth power, and there we go. Okay? So hopefully that helps you guys out, and I didn't confuse you with some other stuff, but there's how when we're given pictures, we can definitely turn them into a sequence if we prefer that. We could take a sequence and turn it into a picture if we prefer that, okay? And if they're arithmetic or geometric, doesn't matter, because we now know how to take that explicit formula from a pattern, okay? All right, guys, there we go.